Richard Rhodes at Atomic Heritage Foundation's studio in Washington, D.C. Can you start by telling us your name?
I'm Richard Rhodes.
And could you spell that, please?
Yes, R-H-O-D-E-S.
Okay, great. Richard spelled the usual way.
Richard spelled the usual way.
Okay, great. All right. We are trying to gather various pieces of information about Hanford, and talk about Hanford, and you wrote that wonderful, huge tract on Hanford. So, but since we're talking about vignettes, we'll have to just compress things a little bit. In terms of how they came to choose Hanford, what were the major factors that made them choose Hanford?
General Groves had established a set of criteria for the several locations of the Manhattan Project. One, that the installations be at least 200 miles from a coast, because at that time it was not yet clear whether the Germans and the Japanese were going to be attacking the United States with intercontinental bombers, I suppose. And 200 miles was considered a sufficient distance, or with an aircraft carrier, to prevent a plane from reaching the site. You didn't want them bombing our bomb sites. So that was one requirement. And then, since we were going to be using large production nuclear reactors to transmute uranium into plutonium at Hanford, or at whatever site the general chose, he knew he'd need a large supply of water, because the energy that was produced from all this fission wasn't going to be used to generate electricity. There wasn't time to worry about developing that technology yet. It was going to be used simply to transmute the uranium. So all the heat had to be dumped somewhere. Therefore, he needed a large river. And then, of course, he wanted isolation. And he wanted isolation for two reasons: to keep it a secret, and also in case something blew up. They didn't know this was new technology, and it was possible that they could have some kind of accident. So those requirements strictly limited the choices in terms of what land was available that the federal government already owned or could easily buy up. And I think he sent out colonels who worked for him to various places around the West. And this particular site in eastern Washington was ideal for those various reasons. The Columbia River went by. It was very sparsely populated. There were some families there who ran orchards. There was a tribe of Indians they would have to be negotiated with. Harold Ickes was head of the Department of the Interior and had been a real thorn in the general's side about negotiating or taking land from the Indians. So that all had to be dealt with, but this was just an ideal place for this particular type of operation. The B reactor was the first of the big production reactors built at Hanford to breed plutonium from uranium-238, which was the advantage of using this technology. U-238 doesn't fission and chain react, and as a result, it's a kind of poison in natural uranium, because what it does do is absorb spare neutrons coming off of fission reactions and makes them unavailable to continue a chain reaction. For that reason, it was kind of an interesting piece of reverse engineering genius to use the poison in terms of a bomb core, the U-238, in its other purpose of making plutonium, and then realizing that plutonium would be an even better material for a bomb than highly enriched uranium or U-235. So that was the basic rationale for building this operation. Using water from the Columbia River meant the water had to be processed. You couldn't just suck the water out of the river. It had to be purified to a pretty high level so that it could then run through this big box of a reactor and keep the place cool and also moderate the neutron reaction. all sorts of support facilities around the reactor, including, most dramatically, the entirely remote controlled processing system that took the slugs of irradiated uranium with their very small but valuable part of the newly bred plutonium, but also full of fission products and therefore intensely radioactive. The slugs would be dropped out of the reactor, pushed through the reactor, and dropped into a big tank of water. That had to be pure. And then the slugs had to be collected up by remote control, carried on lead-lined casks on a remote-controlled railroad, and taken over to the other facilities where the separation process was conducted to get the plutonium, chemically remove it from the uranium matrix. When General Groves went looking for an American corporation to handle this entirely new technology, I mean, no one had run a nuclear reactor of this size before. Certainly the processing of plutonium from uranium had only been done at laboratory scale. It was really one of the amazing tasks of the Chicago branch of the Manhattan Project that they scaled up from basically microsamples of plutonium and uranium to this enormous facility, and did it successfully. This was Glenn Seaborg, who was the Nobel laureate for having discovered plutonium itself and naming it, as people do when they discover an element. But even so, a lot of people weren't sure at all that even Seaborg, with all of his skills, could make that degree of scale up 1,000,000 times or more. But he did, and it worked. DuPont had to deal. General Groves went then to the company he felt could handle the problem, which was DuPont, the great chemical firm. And DuPont was really wary. They didn't want, during the First World War, had made munitions, explosives, and they had been roundly criticized afterwards in congressional hearings and so forth as merchants of death. They didn't want to be merchants of death again with an even new and bigger explosive, nuclear explosives. Groves basically leaned on them, as only General Groves could do, and insisted that they must do this task patriotically. And their final contract specified basically that they would be indemnified against all harm, and that they would be paid $1 a year for carrying out this enormous operation. Basically, they did it at cost. They were concerned, nevertheless, for the health of the many, many people who worked at Hanford and tried to, within the limits of the science of radiation health of the time, to make sure that people were not exposed to excessive doses of radioactivity. They did that, for example, by making sure that the chimneys that vented some of the radioactive steam from their operations were several hundred feet high, and did some meteorology to study the wind patterns to make sure that the gases would be dispersed to a sufficient degree to lower the radioactivity of any amount of that gas to something that would be safe. Everyone was badged, and their badges were checked regularly to see what kind of exposures they'd had in the course of their work. So at every level they could think of, they tried to make sure that the people who were working there and the people who lived around the installation, there weren't many, but there were some, were not exposed to doses more than the normal natural radioactive background in various places around the country. Nuclear fission was discovered in Nazi Germany just at Christmas time in 1938, and the news was published in a German and then an English scientific journal early in 1939. The first experiments to see if you could build what we would today call a nuclear reactor were done at Columbia University in New York by Enrico Fermi and a Hungarian emigre scientist, Leo Szilard. And they very quickly realized that there was a multiplication of neutrons if you put a slug of metal uranium into a tank of water and either use the water to slow the neutrons down by bouncing them around until they could be caught by another uranium atom. Or you could also do the same thing with any light element. And Fermi's first experiments toward building a functioning nuclear reactor involved using blocks of graphite. The closest I think most of us come to seeing graphite in our normal lives is pencil lead, which is fairly pure graphite. That's what the material is. It's greasy to the touch, it's light, it's mostly carbon, and it's a very good moderator, meaning slowing downer of neutrons. And to make a nuclear reactor, you need to slow the neutrons down for technical reasons I don't need to go into, but you can't use the neutron as it comes off of a fission reaction. It's going too fast. It gets involved with other things that you don't want to have happen. In a bomb, you want fast neutrons, but in a reactor, you want them slowed down. So graphite very early on was considered as a material that would help you build a nuclear reactor. In fact, Fermi called these exponential piles that he was building piles because they were literally piles of graphite blocks interspersed with slugs of uranium arranged in a kind of a matrix, sort of a flattened sphere plugged into these various blocks of graphite at a standard distance one from another. So if you were getting a spontaneous fission in a piece of uranium and that produced a couple neutrons, they would bounce around kind of like billiard balls on a billiard table among the carbon atoms until they slowed down enough to be captured by another uranium atom. So that's why they were arranged the way they were. All right. The discovery was made in Nazi Germany. Germany had good scientists. Werner Heisenberg, most famously, was one of the founders of quantum mechanics, one of the real revolutions of 20th century physics. He was there. A number of other good German scientists, including the radiochemist Otto Hahn and his graduate assistant, Fritz Strassmann, who had actually discovered the fission reaction. Many of the scientists who began working on the American project early in the 1940s were actually Jewish escapees from Nazi Germany. They had gotten out really just in time before the whole Hitlerian restriction and eventually murder of the Jews had begun. But they were fully aware that they had to get out of their country or they were not going to be able to continue, certainly their work at that point. So we had a fund of people beginning work on the atomic bomb program in the United States who were not only first-class physicists, but also had intimate experience with what a Nazi regime was like, and also were aware that there were good physicists who were not Jews left in Germany, who might well have been making the same systematic research and discoveries that they were making about what happens with this fascinating new reaction, nuclear fission. It worried them greatly, and it's the reason some of the Hungarian Jewish scientists who had come through Germany in the course of coming to the United States went finally through Albert Einstein to President Roosevelt to start the whole thing going. They were very worried about Hitler getting the bomb before the rest of the world did. One of them said later, the idea of a Third Reich dominating the world for 1,000 years with nuclear weapons was terrifying. The question then was, were the Germans actually working on a bomb? And I think the first answer is yes at the beginning. At the beginning, you didn't start building a bomb. You had to do the basic science behind all of these different reactions at different levels of purity of uranium and different kinds of isotopes of uranium. It was an extremely complicated business to figure out which part of natural uranium you could actually make a bomb with. And then later, with the discovery that if you irradiated uranium, you could breed plutonium, a new man-made element, and that plutonium could be used to make a bomb. These were all stages along the way, and it took a while. But there was no reason to think that the Germans weren't working on the same thing that we were in this country. And if they were, and if they had started when they discovered fission, then possibly they could be a year or more ahead. I think people don't really understand at this late date, so many years afterwards, that we didn't build some bombs to drop on the Japanese. We started working on atomic bombs because we were terrified that Germany was working on atomic bombs, and we knew that whoever got there first could dominate the rest of the world, could even reverse a defeat, as someone said about the whole German program. But at a crucial point, when the Germans were looking at the use of graphite to make what Fermi called a pile, a reactor, they didn't really understand what purity levels they had to get the graphite to in order for it to work. If it were impure with other elements that might absorb neutrons rather than reflecting them, in a way graphite does not, then if they were making measurements with that impure graphite, they might come to the conclusion that you couldn't have a divergent chain reaction. And if you couldn't have a divergent chain reaction, you couldn't have a reactor, you couldn't have a bomb. Nature would have designed things in a way that wouldn't make atomic bombs possible. So it was crucial that you understood that you needed pure graphite. And evidently the Germans didn't understand that for reasons I've not seen in the record. Perhaps their physicists didn't talk to their chemists. There was at least one speculation that one of the German scientists deliberately falsified the measurements in graphite, hoping to stop a German bomb program. I don't think there's really evidence to support that. It seems to have been a mistake in the course of developing these various components of the technology. In any case, it led the Germans to think that they would need several tons of highly enriched uranium to make a bomb. The German scientists still believed that as late as the announcement of the Hiroshima bomb in 1945, by which time they were confined to a semi-prison facility in a country house in England. The war was over in Germany, they had been grabbed by the British intelligence people and stored away in a place called Farm Hall. They didn't know that the entire house was bugged. And when the news came over the radio of the atomic bombing of Hiroshima, there was a great stir among the German scientists because they hadn't even started working on a bomb, really. And they found it hard to believe that the United States had succeeded because, importantly, they assumed it would take tons of highly enriched uranium, which was well beyond the capacity of any country to make. It would have taken, as one scientist said, factories as large as the United States to make that much uranium-235. So then within a couple days, Werner Heisenberg thought it through. Well, if the Americans had a bomb, then that must be too much material. We must have gotten it wrong. And he started thinking it through. And within a couple days, he gave his colleagues at Farm Hall a lecture. And he had the bomb mass about right, 125 pounds of highly enriched uranium. So he thought it through, but they didn't think it through in 1941. And in addition, Hitler was not really interested in the atomic bomb. He didn't understand it. He thought scientists were crazy people. He was much more excited by rockets. And thus, the V-1 and the V-2 rockets were built without a nuclear warhead. And to send a rocket that cost as much as a bomber up into the sky and down on London with just an ordinary high explosive warhead the British called it their secret weapon because it cost the Germans so much. Whereas if you build a bomber, theoretically it can drop bombs, go home, load up, drop some more, go back and forth. Much more economical of money. So the graphite, the graphite measurement, and it's really interesting that science works this way. The graphite measurement may have diverted the German bomb program into the pursuit of building a power reactor, which they decided to do rather than using graphite. But they decided to use a rare isotope of water called heavy water, which has some neutrons in it as well as hydrogen and oxygen. It's a very rare material that has to be typically distilled out of thousands and thousands of gallons of ordinary water. But it has the property of reflecting neutrons very, very efficiently. And by the end of the war, Heisenberg and Otto Hahn and the other first-class scientists who had originally started working toward a bomb were building a half-sized nuclear reactor using heavy water and cubes of uranium metal hung on chains, really very interesting and exotic design, into this tank of heavy water to form this matrix that I was talking about of blocks of uranium separated by a material that would slow down the neutrons. And when the American intelligence group that was looking for these people to make sure they weren't working on the bomb found them in a little town called Hagerlach, they found this in a cave. They found this little half-size reactor, which if it had been doubled in scale, would have been able to go critical and actually produce a controlled chain reaction. So they weren't even at the stage yet where they had their first reactor operating. General Groves was not only in charge of the Manhattan Project, but in a sense he was in charge of the whole government effort around nuclear fission and bombs and reactors and so on. He was a general of the Army Corps of Engineers. One of his concerns, therefore, was what was the enemy doing? Where were they in their program, if any, in relation to the United States and its program? They, meaning both the Japanese and the Germans. Just to speak briefly about the Japanese, they really never got beyond a little bit of laboratory research because they realized that the scale of factory that they would have to build to either enrich uranium or to breed plutonium, but particularly to enrich uranium, would use up something like 1/3 of their entire national electrical supply just to operate the machinery, and would use more than their annual production of copper to make the wires to wind the magnets for one version of uranium enrichment. They simply didn't see how they could make it happen in time of war. So they never got very far. They never got beyond some laboratory research in various technologies for enriching uranium. So we can set them aside. Germany, however, was another question. Again, because we knew that the discovery itself had been made in Germany. We knew that Germany had first-rate scientists. And it seemed logical that Hitler, with his interest in new, fancy new weapons, would be interested in atomic bombs. So one of the things Groves did was put together a special mission group of Army personnel and scientists, interestingly, who were not knowledgeable about the Manhattan Project, because Groves was a very logical man. He figured if he used someone who knew about the United States program, and this man were captured and, let's say, tortured by the Gestapo, that he might tell the Germans about our program. So he found a physicist who was a nuclear physicist and knowledgeable about nuclear physics, but was not privy to the secrets of the US bomb program. Thus, if he were kidnapped and or captured and tortured, that he wouldn't be able to tell them anything more than this is how neutrons work with uranium or whatever. So this group, which was called the Alsos mission, which is a pun on the Latin word for Grove, General Groves, was sent over to Europe, and they followed just behind the lines of the advancing United States Army as it moved toward and into and through Germany in the last months of the war. I think in the fall of 1945, the Alsace people actually started their effort. They had a couple of assignments. The most important was to find out whether there was a German bomb program. And again, because Groves thought in such a logical way, he was a real engineer, MIT trained engineer, General Groves. He wanted to know the whereabouts of all the uranium ore, which he knew had been in Belgium from the Belgian Congo, where there is a lot of uranium in the ground at the beginning of the war. His logic was this: when I know where all the uranium ore is, I'll know that they didn't build the bomb, because you had to have ore to build a bomb. And that's the only source that they could have used for their ore. So that was another task of the Alsace mission. And a third task, and a very important one, was, from Groves' point of view, was to grab all the German atomic scientists and take them back to the United States so the Soviet Union wouldn't grab them and take them to the Soviet Union and use them to build a Russian bomb. Groves was thinking ahead, if you will, to what we were not yet calling the Cold War. So this team of people went over there and found their way around, and the first thing they found in, I think, Frankfurt was a whole laboratory and a lot of documents that gave them a pretty good idea of where the German bomb program was. And where it was basically nowhere. They had not got beyond the idea of building reactors and hadn't yet figured out how you would even do a bomb, much less move much in the direction of actually making the crucial materials, uranium or plutonium. And then as they penetrated further in, they finally were able to track down the various atomic scientists, the Germans, and grab them. Most of them, not all of them. Some of them were grabbed by an almost identical team that the Soviet Union had sent with some of its scientists to do basically the same thing. There was a time when they were both in Berlin at the same time, almost. I think they missed each other by 48 hours. They were grabbing a bunch of very high concentrate uranium ore that both sides knew had been stored in a particular warehouse in Berlin. And the Soviet team got a few more tons than we did, but basically they went in opposite directions and took this valuable material back to their home countries. So the Alsace mission was an important mission, and by the time they were through, which was presumably close to May 45, General Groves had his absolute evidence in the form of uranium ore that had not been used, that there was not going to be a German bomb, and he could rest easy at that point. When the Alsace mission incontrovertibly demonstrated that there was no German bomb program, or at least no German bomb, there'd been sort of a program. Many of the scientists who had worked on the Manhattan Project, particularly the ones at Los Alamos and at the University of Chicago, particularly the emigre Jews from Europe, whose primary concern had been they didn't want Hitler to get the bomb, were presented with a dilemma. Should we continue working on this weapon of mass destruction? Our original intention has been met. We don't need to build a bomb to have as a deterrent against a German bomb. What do we do now? Now, most of the work by that time was finished at Chicago and in Oak Ridge. They were wrapping up the development of the production of uranium and plutonium for the weapons. The focus of work by the beginning of the summer of 45 was Los Alamos, where the scientists were actually designing and building by hand the first 3 atomic bombs. The one that was tested in the desert in New Mexico in July 1945, the one that was dropped on Hiroshima, the one that was dropped on Nagasaki. Those scientists were so busy trying to get the job done. I mean, from Groves' point of view, trying to get the job done before the war was over. He didn't want to have to face a congressional committee, as he said, having spent in those days, $2 billion of federal funds, the equivalent of about 25 billion today, on a weapon that was not ready in time to use. He told one of his colleagues, we'll all spend the rest of our lives in Leavenworth prison. So it was important to Groves that this job got done in time to use these weapons on the battlefield or wherever. Those scientists were then so busy working basically 7 days a week, day and night. They really, as they said later, didn't have time to think through these other questions. But the ones in Chicago, and to some degree the ones at Oak Ridge and at Hanford, had a little more time at least, and could begin to think, is this right? Is this wrong? Should we use these weapons without telling our allies, the Soviet Union? The Danish scientist Niels Bohr, who was one of the great philosophers of the 20th century, as well as one of the great physicists, had come through Los Alamos in 1940, late 43 and early 44, and had raised the whole question of, well, if you spring this surprise on the Soviet Union, aren't they going to feel that you are building this as much against them as you are against Japan or Germany? Shouldn't there be a discussion ahead of the use of these weapons with our allies about this new and fundamental change in the scale of potential destruction in war? Unfortunately, although he spoke, Bohr did, with both Roosevelt and Churchill in particular didn't like the idea at all, didn't see the reason for doing it, wanted to keep his special relationship with the United States. Remember, Great Britain was almost bankrupt by the end of the Second World War. So Bohr didn't get anywhere with that idea, but it was out of ideas like Bohr's that this general feeling came, in Chicago, particularly among the scientists there, that we ought at least to tell the Russians. Maybe we should warn the Japanese before we drop a huge destructive firebomb on a civilian city. And this leads to a very complicated story about the end of the war. But my point is simply, there was a dramatic change with the end of the war in Europe about what do we now do with these bombs that we've been building. And there is as well no question that General Groves and the Army had no doubt at all that if we're not going to use them in Germany because Germany surrendered, we are damn certainly going to use them in Japan if the Japanese don't surrender. And of course we did. The problem with the use of the atomic bomb in Japan, I think, centers on two issues that what I would call revisionist historians have raised. One has to do with whether the bomb was necessary. Were the Japanese prepared to surrender just at that point? And were the bombs in some sense superfluous? Dropped in the middle of the Japanese supposed effort to try to communicate an agreement to surrender with a country at which they were at war and therefore had no diplomatic relations, and as they eventually did do, working through the Swiss. That's one question. The other question is, should we have dropped these bombs on civilian cities, Hiroshima, Nagasaki? The two questions are, to some degree, a diversion from what was happening at the time, which was this extraordinary resistance of the Japanese leadership to surrendering at a time when they had been, by any measure of normal warfare, roundly defeated. They had no air force. They had no navy. Those had both been destroyed. They had a considerable land army on the ground in Manchuria, but it really wasn't going to be of much use to them if we invaded their home islands. Their people were down to about 1,000 calories a day of the worst kind of weeds and buckwheat and anything they could get their hands on to eat. We couldn't understand why they were refusing to surrender. I mean, of course, it turned to some degree on their concern that we would execute their emperor, refuse to allow him to continue to be the titular head of the nation, the spiritual head of the nation. And these were valid issues. There had been a great deal of debate within the State Department about whether or not to force the Japanese to give up their emperor system or not. One of the State Department's leaders in that argument was the poet Archibald MacLeish, who was also an American diplomat and who insisted we should force a democratic government on the Japanese. In the end, of course, we did understand that the only way really to get all the Japanese soldiers still scattered around the Pacific to lay down their arms was for the emperor to order them to. And under those circumstances, we kept the emperor system, but at the same time installed a democratic system under that. That was the work of General MacArthur and his team after the war. But it turns out that none of these issues were really what was bothering the Japanese. They weren't ready to surrender, the military leadership. And it was because they felt they still had a chance to force the United States to more acceptable surrender terms. Not an unconditional surrender, as we had been insisting on, but a conditional surrender that might give them, let's say, some of the possessions they'd acquired in the course of the war in Asia, for example. They imagined that if we had to invade their home islands and they resisted strongly enough, we would take such a bloodying as we already had on Okinawa and Iwo Jima, where we'd lost men to truly suicidal forces on the Japanese side, that we would not have the stomach to continue fighting and would be willing to make some kind of deal that would be better from their point of view. Until quite recently, until just a few years ago, I think it was the general consensus of people who'd looked at the documents that the atomic bombs did contribute to the emperor's decision for the first time in history to step into politics rather than to remain separate and aloof and kind of the final person who agreed to what the political system had already decided on. And that was the result of his horror at the atomic bombings. A Japanese-American historian who carefully looked at the Soviet, Japanese, and American records around the turn of the 21st century, I think I established, from my point of view, convincingly, that the real turning point was the decision of the Soviet Union, which had been neutral on its eastern front against the Japanese, to enter the war on the 8th of August 1945. When the Japanese military realized that it was basically now surrounded on two sides by fresh, powerful armies, then they understood that the war was over. And at that point, the emperor was able to use the fact of the atomic bombings as an excuse for the surrender. Rather than saying, my people failed, he said in his speech to the Japanese people on the 15th of August, a new and most terrible weapon of war has been introduced into the scheme of things, leading us to do the unthinkable and agree to surrender. So the bombs had their influence, but they were not the decisive issue as far as why the Japanese agreed to an unconditional surrender. The other part of the question of the atomic bombings of Japan has generally been a feeling that it was somehow horrible and immoral that we used these bombs over cities filled with civilians. The United States Air Force's official argument has been over the years that, in fact, because manufacturing of war materials was distributed in Japanese cities. I mean, a lot of work went on in people's homes with little hand presses and lathes and so forth. That, in a sense, these were military targets. I think that's stretching it a bit. They were targets of civilians. But this takes us back to a larger issue. And in a sense, this question was decided long before 1945. Strategic bombing was a whole elaborate theory that was developed out of the horror of the trenches in the First World War, which ran down the length of Europe and where 20 million people slowly died in various battles, with the front line hardly moving in either direction, a few kilometers either way for the whole 3-4 years of the First World War. There was an Italian theorist of air power named Dewey who theorized that if you could use planes carrying bombs, you could basically fly over the front lines and attack the civilian production of war material in the homelands behind the lines. The theory was that if you caused enough destruction, that the people would rise up in revolution, overthrow their warlike leaders, and sue for peace, which I think never happened in the history of strategic bombing. It certainly didn't happen in Spain during the Spanish Civil War, when a lot of this city-busting technology was actually first tried out by German forces fighting on the side of Franco, the places like the famous town of Guernica, where they deliberately firebombed the city to utter destruction. It had nothing in it at all except some peasants who'd come to market that day. But the Germans were trying out the technology because they believed the theory. And it gave let's face it gave the Air Force something to do. So our Air Force, the United States Air Force, had been active all through the Second World War, enlarging the technology of strategic bombing. I mean, the fact that the Germans first tried it out in Spain in 1937 and 1938 came back to haunt them during the Second World War, because we systematically destroyed city after city in Germany with firebombing techniques that occasionally would start a mass fire, like a tornado, where the fires coalesced into one huge fire, sucking in air from around the edges of the firestorm and having it chimney up in a cycle like that basically burned out everything organic for square miles around. When we then got to the question of what to do with Japan, before we had invaded the home country, the Air Force wanted to use its technologies to help win the war, of course, and tried precision bombing of factories. But no one knew at that time about something called the jet stream. And the new big B-29 bombers that had just come into use in Japan in 1944 were flying at 29 and 30,000 feet and bombing from that altitude, not really understanding that the wind of the jet stream was going to blow them 10 or 15 miles off course. The Japanese had a sort of joke. At one point, the Japanese could be very ironic about the destruction that was being visited upon them. One of the first attempts at bombing, strategic bombing north of Tokyo, the bombs landed in Tokyo Bay. And the Japanese joke was, the Americans are trying to drown us. So pinpoint bombing didn't work. And the logical next step was then to go to area bombing. And by April of 1945, Curtis LeMay and his fleet of several thousand B-29s were flying almost wingtip to wingtip at 5,000 feet below where the Japanese anti-aircraft guns could target, and just systematically dropping incendiaries to make kindling, dropping firebombs to start firestorms, and burning out Japanese cities one after another. The largest death toll in any single city in Japan was in Tokyo in April 1945, the first of the big firebombings, when there happened to be a very high 30-knot wind blowing across the city that started a huge firestorm, killed easily 100, maybe 200,000 people, burned them to death that one night in Tokyo as a result of this 6-pound incendiary bomb technology. By the time the atomic bombs were ready at the beginning of August 1945, the US Air Force was down to Japanese cities of less than 50,000 population. Everything else was already destroyed. And for the people who were developing the bombs and for the Air Force, these bombs didn't seem to be larger in order of magnitude of destructive capability than these massed firebombings that had already been going on. The one difference, of course, was that the bombs would produce radioactivity. They were deliberately built with timers that would set them off at 1,800 yards above ground, so that the fireball that forms when a nuclear explosion occurs would expand, would not touch the ground in the course of its hot expansion. And touching the ground, of course, would have irradiated dirt and soil and made a very intensely radioactive mess all over the city that would have killed a lot of people with radiation. We didn't want to do that. We wanted these bombs to work just like the incendiary and high explosive bombs that the Air Force had already been using. We wanted blast and fire, but not radiation. And there was very little actually radiation other than the immediate prompt radiation from the fireball at either Hiroshima or Nagasaki. Most of the deaths, people I think don't realize this, most of the deaths were from fire because of this mass firestorm that the bomb started in both cities. So from the perspective of the military, using atomic bombs in August 1945 in the pursuit of ending the war was not different morally, and I dare say it wasn't different morally, from what had already been going on all over Europe, had been going on all over Japan. It's what we had been doing for a long time. If there was a moral decision, it was made back in 43 when we switched in Europe from trying to do pinpoint precision bombing, which we couldn't do for various technical reasons, to mass area bombing with the concomitant civilian casualties. It's a very important point because, school children these days have this kind of package that they go through of the trial of Harry Truman, the impeachment of President Harry Truman for atomic bombing the Japanese. But if that were going to be a realistic experience for these school children, they should go back to Guernica. They should go back to Hamburg. They should go back to when this really started and find out why. It wasn't because we were just bad guys. It was because we had a problem, a very difficult military problem to solve. So it's irrelevant from my point of view how many lives were saved of American troops that would have been lost had we invaded the Japanese home island. Those issues that historians have squabbled about now for 40 years. The question is, what were they trying to do? Had we done it before? And the answer is yes, we had. We'd already worked all that through. This was just more of the same. The discovery of how to release the energy locked up in the nuclei of atoms was a discovery as momentous as the discovery of fire. That's a big statement, but I think it's valid. Nuclear energy was the first major source of energy humankind had found that does not directly or indirectly depend on sunlight. Coal ultimately derives from sunlight. Wood, of course. There's a little bit of energy in the geothermal drilling down deep into the earth, and that's actually driven by nuclear fission of uranium and the decay of uranium atoms in the core of the earth, believe it or not, which is why it's still around after all these billions of years. It would have cooled long ago if there weren't some active process making new heat down there, and the process is actually decay of elements similar to fission. So here was this new, deeply fundamental change, as Niels Bohr put it, in the course of human affairs, destined, as he understood almost immediately, to bring fundamental changes to things you would not think of in terms of energy. The relationship between nation states was affected. Because if both two countries have nuclear weapons, they just simply can't go to war with each other. If they do, they'll destroy each other. That's not the point of a war. The point of a war is to win a victory of some kind. One side and the other side loses. But if both sides are destroyed, then war is pointless. There's a reason why we have had no world-scale wars since 1945. And I think that reason is the introduction of this fundamental change in our relationship with nature, called the discovery of nuclear fission, and in the course of time, the application of fission to making fusion work, hydrogen bombs, if you will. I'm not saying the weapons themselves keep the peace, although for some time now that's the way we played it, but at great risk. I am saying that the fact that this technology makes it possible to have mutually assured destruction, as it was called, whether it's at the level of knowing how to build these weapons or at the level of actually having arsenals full of them, that's made a deep and fundamental change in human affairs. Who did this? How did this happen? At the beginning, it happened because of a very unusual profession and kind of knowledge and way of approaching knowledge called science. Science traditionally has worked by what anthropologists call gift exchange. That is to say, if I make a discovery in the course of my research as a scientist, I publish the results. That's how I got credit for them. My work doesn't pay me other than whatever I might earn as a university professor or someone in a laboratory, whatever. So the payment is in the reward, the recognition for having made a discovery. You can see this in the fact that a lot of elements are named after their discoverers. That's really something very special. There are only 92 on the periodic table, naturally formed elements on Earth. So I give the world the gift of the knowledge of this discovery I've made. Other scientists who read these journals take that knowledge, and if they're working in a similar field close to mine, they may use that to begin looking further into that part of the natural world. And that may lead to another discovery, which they then publish, and then I take that and I use that to further my work. So science is an open world, as Bohr called it, of gift exchange among people who share knowledge in order to advance knowledge. That meant when fission was discovered in Nazi Germany in December 1938, Otto Hahn and Fritz Strassmann, the two radiochemists who made the discovery, published a paper about that research, how they did that, and what the results were. That paper was first published in a German scientific journal, which was read all over the world, and then further refinement of the information was published in the British journal Nature. Scientists everywhere in the world who were working in nuclear physics immediately, really immediately, within a week or two, realized you could probably build a nuclear reactor using this new discovery. You could probably build an atomic bomb. And research programs started up in France, in Germany, in England, in the United States, in Japan, everywhere that the science of nuclear physics was far enough advanced that there were scientists capable of understanding the discovery. Research began on it and what it meant and how it worked and how you might make it do more than just split an atom and so forth. In fact, interestingly, one of the ways the Soviet Union scientists realized that the United States was working on an atomic bomb once that program began 1940, 1941, was when the papers of all the famous nuclear physicists in the United States stopped appearing in the journals. They stopped giving away their information because now it was a military secret. And one of the more astute Soviet scientists said, they must be working on a weapon. So this process of sharing knowledge in order to advance science meant that there was a kind of international community of scientists who were knowledgeable in this field. Adolf Hitler made the really deeply stupid mistake, he and his colleagues, of deciding that this kind of physics was somehow besmirched and Jewish. Well, this was an artifact of the fact that physics in the 19th century was somehow construed by German philosophers to be a sort of a materialistic science, not as spiritual as I don't know, whatever they were working on, archaeology or whatever. And as a result, it was one of the few fields of science that Jews were allowed to study at the university. Nobody else really wanted to because it was looked down upon as somehow vulgar and Jewish. And so the results, having been worked on by Jews of the level of intelligence of Albert Einstein, were discredited in some way in the official Nazi canon of rules about who's good and who's bad in the world as Jewish physics and not of interest, really. And more importantly, when the Hitler regime came into power in 1933, they nationalized all the universities, making all university professorships and other positions civil service positions. And then they passed a law that said no Jews in the German civil service, and thus basically threw every Jewish scientist in all the universities in Germany out of a job. And they couldn't find any other work either. So what could they do? They could immigrate. And there were nonprofit organizations in England and in the United States and universities that realized these were first-class scientists and wanted them to come to their universities and their countries. And in this way, toward the end of the 1930s, just before the beginning of the Second World War, Great Britain and the United States acquired a whole cadre of really of Nobel laureate level scientists, if you will. People like Hans Bethe, people like Eugene Wigner, and many others besides, who Einstein had come over years before, as a matter of fact. He'd realized earlier than most what was brewing in Germany and didn't see any reason to stay. So these emigres arrived in England and the United States grateful to these countries that had been willing to accept them and to incorporate them into their communities of science and of generally of life, and were all the more prepared and concerned to help their newly adopted countries build the bomb ahead of what they presumed was a German bomb program. So when you went to the various parts of the Manhattan Project, whether the original place in New York City at Columbia University, where they were working on both a potential nuclear reactor and also possible ways to separate out the bomb material part of uranium from the poison part of uranium, the U-235 from the U-238, or at the University of Chicago, where they were basically working on the whole chemistry of plutonium, whether you could build a reactor, and if so, if you could use the material in that reactor to breed plutonium for a bomb. Or a bit later, Hanford, Oak Ridge, and Los Alamos, which the Corps of Engineers then built in order to actually make the materials and design the weapons themselves. These were rich collections of people from many different countries with a basic core of Native American, I mean, of course, American citizens, born American citizens, working with these brilliant people from around the world. I don't think it would have been possible to build the bomb, certainly not before the end of the Second World War, without the vital contribution of all of these various immigrants who joined the program. There was a crucial point in the program at Los Alamos in the summer of 1944 when it was realized that plutonium, of which you needed a lot less than highly enriched uranium to make a bomb, was so fissile that if you tried to use the standard design that was going to be used for the uranium bomb, which was basically a 3-inch Navy cannon about 6 feet long, with one piece of uranium attached to the muzzle and another piece as a sort of bullet fired up the barrel to mate with the other piece to make a critical mass and start the bomb going. That if you tried to do that with plutonium, they discovered that summer, this piece would melt down before it even got up to the other end of the barrel, even if it were fired at 3,000 feet per second. That's how reactive plutonium was. And then they realized that they were going to have to invent an entirely new technology. One that would involve taking a solid ball of plutonium that was just subcritical, not quite enough to start a chain reaction, which is a function not only of the geometry and of the state, whether it's a metal or an oxide or something, but also of the density of the metal. That they were going to have to figure out a way to take a solid ball of plutonium, squeeze it with high explosives to a greater density, almost double its normal density. In other words, squeeze that ball until instead of being about this big, it's only about this big, thereby pushing the atoms of plutonium closer together and making the chain reaction possible, making, if you will, the critical mass much smaller because it's denser. Somehow they were going to have to do that, and they were going to have to do it in about 8 months if they were going to be ready with the plutonium bomb. And if they weren't going to be ready with the plutonium bomb, they would only have one bomb in August of 1945, because it was such a laborious process to make highly enriched uranium out of natural uranium, that's all the uranium they'd been able to accumulate by August of 1945, about 125 pounds. Enough for one gun bomb, the bomb that was used on Hiroshima. Then they needed some help with the complicated mathematical calculations that were involved in figuring out how to shape big blocks of high explosive in such a way that a divergent explosion, like most explosions, could somehow be turned around and focused inward on a point, which would be the center of this ball of plutonium. And if you build your shaped charges and use explosives that burn at different rates, some fast, some slow, you can actually do that. But the geometry was immensely complicated. There were no computers yet, and they needed brains to do the computing. And there weren't enough people at Los Alamos who were busy working on the gun bomb, mostly, to get the job done. And at that point, they turned to the British. And another whole contingent of immigrants to Britain from Nazi Germany and other parts of Europe, plus the British scientists themselves, arrived at Los Alamos to help out. And obviously got the job done. Indeed, the person who really did the geometry of that bomb was the famous Hungarian mathematician John von Neumann, who had the mathematical skills without a computer to help to figure out the complicated geometry of this new system. That was so uncertain even then that the system would work. And there was enough spare plutonium available that they tested that bomb. That was the first atomic bomb explosion in the desert in New Mexico on July 16, 1945. This was a work of many people, and not only at the level of the scientists. Factory workers came in, young women who had been living in Tennessee through the Depression came in to run these giant machines that were using magnets and other systems to enrich uranium. They weren't even told what the machines did. They were put in front of a giant gauge with a needle and told to keep the needle between those 2 points. Don't let it go outside by spinning these dials. And they got very, very good at it. In fact, I talked to people who worked at Oak Ridge in these basically factory jobs, and they said, the Depression was so boring. There wasn't anything to do. We didn't have any money. We couldn't even afford to go to the movies. And then suddenly, here is this interesting work. We had tennis courts. At night, they took down the nets and they turned them into dance floors. I mean, there were a lot of babies conceived at these places around the country in the course of the Second World War. General Groves at one point called Robert Oppenheimer in at Los Alamos and said, "You've got to stop these people having so many babies. And they're overrunning our hospital system here. We don't have room for them all." And Oppenheimer said something like, "General Groves, that's outside my bailiwick, I'm afraid. I don't really have any control over that." So this was a time of great excitement, a time of great purpose, a time for many of realization that, particularly the young men who were involved, the scientists, for example, the average age at Los Alamos among the scientists was something like 27. Oppenheimer was only in his mid to late 30s. They were a very young crowd. And they understood that if they weren't there working on this special weapon, they would be on the front lines in Iwo Jima or in France or in Germany. They would be risking their lives in another way. They took that very seriously. They realized that other lives depended on the work they were doing because they did believe, and I think correctly, that when these bombs were built, the war would be over. As Oppenheimer told them, maybe all wars would be over. So at every level, excitement, intensity, a feeling of responsibility, a feeling of great moment in the work they were doing, all of which was quite true. They were doing something absolutely revolutionary. And it did change the way the world has worked ever since. One of the persistent, I think, misapprehensions about the development of the atomic bombs is that in some way, if the scientists had all gotten together, they could have decided, oh, let's keep this a secret. Let's not tell anybody about it. This is not a good thing for the world. It's going to cause a lot of trouble. Let's just go home and stop working on this. But science doesn't work that way. First of all, on a larger scale, if you stop scientists from communicating with each other, something General Groves had a lot of trouble with during the war, because he didn't want people to, he wanted to compartmentalize everybody and let them only know what they needed to know to do their specific part of the job. And that worked fine for the women who were running the big dials at the factory down in Oak Ridge, but it wouldn't work with the scientists because they had to communicate their discoveries to each other in order to continue pursuing the cutting edge of what they were doing. And similarly, when nuclear fission was discovered, it was published. The information about the discovery was made public. That's the way science works. But also, there wasn't a war on then. There was no reason anybody might have thought of to keep it a secret. Once they realized that there was a weapon possible, and once the war began, then the work that was done subsequent to that point was indeed kept secret. Much to the detriment in the short run of the development of the science of nuclear physics, but that all got straightened out at the end of the war. But the point is, this was knowledge. Science had reached that point, the science of nuclear physics. People had been working for about 3 years on this mysterious mix of stuff that happened when you bombarded your solution of uranium nitrate with neutrons. All sorts of radioactivities would come out of it. Different elements would come out of it as you sorted through this material. And people didn't understand what was going on. Once the discovery was announced, everyone who'd been working in the field ran to their laboratories, grabbed some equipment off the shelf, ran the reaction, and there it was, and then kicked themselves for not having made the discovery. I remember talking with Glenn Seaborg, later a Nobel laureate for the discovery of plutonium. Seaborg spent 3 days, he told me, in an absolute blue funk. He was an immensely ambitious man. He wanted to make world-changing discoveries, and to have missed this one that was right before his eyes because he just didn't know what he was looking at galled him terribly. But it was only once that discovery was out there that everyone then immediately realized that they were on the verge of discovering it anyway. And if it hadn't been discovered in Berlin, December 1938, it would have been discovered at Berkeley or in Paris or in Cambridge, England. Everybody was there because they were all working together. We're all familiar with the phenomenon of two labs coming in with almost identical results 3 hours apart from each other, or 2 days. And the priority goes to whichever one got the news out first. That's the way science works. People are working right on the edge of making these discoveries. So to say that if these guys had, once this discovery was made, they all could have gotten together and said, let's forget about it, is frankly ignorant. It just doesn't comprehend the way science works. If, on the other hand, you decided that all scientific discoveries should be kept secret until their moral and ethical possibilities are examined by whomever would be credited with doing that, well, then science would stop. Because it's by knowing what other discoveries have just been made in a particular field that you're able to make the next advance and the next advance. So Niels Bohr, who's really a hero of mine, once said that the goal of science is not power over nature, which is what we tend to think of it as. It's rather, he said, the gradual diminution of prejudice. And that sounds innocuous till you start thinking about it. He's talking about the prejudice that the Earth is at the center of the universe, which most of the world believed until Galileo and Copernicus and so forth proved definitively that the sun is at the center of our little solar system, and that we're just on the edge of a lot of other galaxies and stars and so forth. That had enormous philosophic consequences for the world. It was part of the dethroning of the belief that we were a special creation of God's, just a little lower than the angels. Well, that was some prejudice that people were relieved of, that the Earth was at the center of the universe. We're still wrestling, at least in the United States, with the question of whether we are a special separate creation, or whether indeed we evolved along with the other mammals and primates as Darwin would have it. Well, that's still an active debate in the United States 150 years after Darwin. So the gradual alleviation of prejudice, there was a prejudice up until 1945 that nation states were absolute entities, and that at their boundaries, if there was a question about what was theirs and what wasn't theirs, they could go to war with other nation states, and that the outcome of such a conflict would define the absolute sovereignty of the nation state again. Well, you can't go to war with nuclear weapons with another nuclear power. And that meant not only that essentially the end of world-scale war since 1945, it also meant that the absolute sovereignty of the nation state had been compromised. It's no longer possible to determine your rules over some other country's rules by going to war with them if they have nuclear weapons and you do too. We see this all the time in in the wars the United States has fought since 1945. We were prepared to lose a war in Vietnam. And the chief negotiator of the Vietnamese government, when he talked to Henry Kissinger at the Paris peace talks, said we knew we could win because we knew you wouldn't use nuclear weapons on us. And everything else we had within our power to do, we were determined to win this fight. So the very simple discovery of releasing nuclear energy led to the continuing evolution of fundamental changes in the relationship among nations and peoples around the world, which is not nearly finished yet. And that's not something that you can put in a box and shove away in the back of the closet.